Oh, thanks for the introduction. Thank you for being here. So actually, this is a side project that I started while trying to formalize a few program calculi in Lean. And while doing this, I noticed that I was doing a lot of copying and pasting. Most of my research is in software engineering, and again, copying and pasting is a sign that we don't have much modularity and reusability. And again, this is where this project started. So again, just to give you a motivating example, this is kind of a subset of formalization of simply typed lambda calculus with two native types, natural numbers and booleans. Again, I only have enough definitions here that would fit on one slide. And again, these are the ones that I'll be using for illustrative purposes. So here we can notice that we can actually decompose or split these definitions into three simpler ones. One for the Boolean type, one for the natural type, and one for the pure simply typed lambda calculus. And as we can see, the definitions for each one of those components are scattered all across the code base. And again, no matter what metric you use, scattering is inversely proportional to modularity and reusability. So ideally, we would like to have definitions that look a little bit like this. Again, to the best of my knowledge, I think Lean still does not have a module system. So here I'm just using namespaces and calling them modules. So sorry for that. So again, if we were to define a Boolean module, it would look like this. And again, this is completely independent of all the other definitions for natural numbers and for simply typed lambda calculus. Again, the net module will look like that. And simply typed lambda calculus, again, it's completely independent of the two native types. Now the question is, how do we compose those independent definitions into something like what I started with at the beginning? And this is where metaprogramming comes into play. So again, the concepts in this project, none of them is actually specific to Lean. But the main reason why I'm using Lean here is because of the metaprogramming facilities provided by the language. So metaprogramming is writing programs that manipulate other programs. So what I actually need to do here, or what I want to add, is something like this vertical bar plus operator. This is user defined. Again, Lean metaprogramming allows you to define your own syntax extensions and to introspect into the definitions of types and functions and generate code. And actually, this is exactly what I'm doing here. So what I'm trying to do in this line is composing boolean.t, nat.t, and stlc.t into a new type called t. And one thing to notice here is if we're just copying the constructors from each of the three, we'll have the types of tau1 and tau2 here to be stlc.t, which is this, while actually what we need is to rewrite this into the new type t. So this is something that needs to be done while doing this composition. The syntax, in addition to kind of unioning the different constructors here, it also allows you to add new constructors. So again, if we have a syntactic category for is0, which would naturally exist only if you have both natural numbers and booleans. So actually, it is a cross-cutting concern between boolean and nat. Then you can actually add it whenever you are composing nat and boolean together. Well, again, we can do the same thing for inductively defined predicates. But actually, one thing to notice here, this is a type relation, and we're composing type relations from Boolean, nat, and STLC. one thing to notice is the types of these components are actually different. So boolean.trl is actually boolean.term to boolean.t and so on. But at the same time, these types here, boolean.term, nat.term, stlc.term, are subtypes of the newly defined type T. So this is safe from type safety point of view. So actually what we end up getting is, because T actually is the sum of these three, there's a missing bar here, I'm sorry. And because term includes these three as well, then this definition is safe. Again, I mentioned subtyping. So one thing to keep in mind is whenever we do this, then the components boolean.t, nat.t, stlc.t are all subtypes of the newly defined type T. And in Lean, we can actually kind of explicitly represent that by generating instances of the coercion type class. So again, these three instances are automatically generated as a part of the implementation of this operator as well. So we have now coercion from the subtypes to the newly defined supertype. So we can actually write something like this safely, and this type checks. Lean also provides another coercion type class called codep for dependent coercion, which can provide us a facility to do coercion in the opposite direction if we have enough information about the structure of the value that we're casting. So again, these three instances are automatically generated as a part of the implementation of the composition operator. So we can do this kind of assignment safely. Again, moving from t.bool to boolean.t. I'm sorry, to t.bool is actually from the newly defined type. Boolean.t is actually the subtype, so we can do that. But again, because if we do an assignment first and then try to do the same thing, it does not type check because we lost the structure information. So far, what I mentioned is all about inductive types, but how about functions? Here, I did not use the term composing functions because, again, obviously, this means something completely different. So for the lack of a better term, I'm just using multiplexing. But the idea is kind of the same. So if we have a function count nodes for Booleans, for NAT, and for SDLC, we can compose them together, again, or multiplex them into a new function count nodes that, again, has all the pattern matching cases from all three, in addition to this new one that we added here. Two things to keep in mind. These component functions, each one of them is recursively calling itself. So we need to change the recursion pattern here to call the newly defined function. And in the implementation, the current implementation, I'm making the very simplifying assumption that the functions that we're composing are all pattern matching on one argument. So again, this is one limitation that I will mention further at the end. The implementation is mainly just, again, leveraging the metaprogramming facilities in Lean. Again, we're having a parser for the extended syntax for type composition and function multiplexing, elaborators for both. We need to keep track of which definitions have been composed or multiplexed in case we use them later on. So actually, we have an environment extension in Lean for this. And then we have the generators for composed types, coercion operators, and function generator for multiplexed functions. So now to the limitations, and I think this is probably the most important slide, because this is still work and development and very early stages. So I still don't have full support for higher order types, index types, dependent types. So I've been doing this on kind of as needed basis. So again, I need to spend more time working on providing full support for each one of these three. And again, the assumption on multiplexing functions, again, I'm assuming that the functions that are being composed are just doing pattern matching, very simple pattern matching on one argument. Again, this is an assumption that should be relaxed. Mutual recursion is not supported right now, but it should be relatively easy to add it. So again, because Lean does not have a module system, ideally this kind of thing is even more usable if we can compose modules right away instead of composing individual definitions. So maybe in a different language with a module system, we can do something like that. Right now, I don't have anything that that deals with theorems of proof objects. But obviously, this will be of much bigger value of what I have so far, because again, reusing pieces of proofs is going to be even more valuable. And finally, in functional multiplexing, what I'm doing right now is copying parts of the implementation into the new one. But this is not really reuse; it's mostly copying. And we're doing this at the surface, just copying pieces of definitions. But for future work, again, one question that I have in mind is, can we do this by calling the functions that we're composing instead of copying them? And to be able to do that, we have two challenges. How do we deal with recursion? Is it maybe, for example, possible to modify fixed point operators to support that? And with too many function calls, how do we deal with the performance cost of that? Can we do inlining at the intermediate representation level, for example? So again, these are all ideas for future work. So that's it for the presentation. Thank you so much for listening, and I'll be happy to take